Okay, let's take a look at this example. In this case, we are going to analyze the variation of a furnace wall temperature. So this furnace is made from carbon steel, so it has properties unknown. Thermal conductivity, density, and heat capacity are given. And we also know the thickness of this wall. So to protect it from the corrosive gases, we include a ceramic film here. So this ceramic film introduces a contact resistance. So we have a contact resistance situation in here. So initially the furnace is at 300 Kelvin, okay, and the gases are at 1300 Kelvin. So the furnace is at 300 Kelvin. So we know the convectivity transfer coefficient H is 25. Okay. So, and we are told that this thickness is so thin that it doesn't have any thermal capacitance. Okay. It doesn't have thermal capacitance. So the question is, how long does it take for inner surface of the steel to reach 1200 Kelvin? And what is the outer surface temperature at this time? Okay, so let's take a look at this problem now. We are trying to find how long does it take TSI to reach 1200 Kelvin, and what is, let's call it as T2 at that time. T2 is the outer, I'm referring to outer surface here. So in this case, we don't know. I mean, we are talking about the lump capacitance method. Now we introduce all of a sudden the concept of resistance. So now the question is, how are we going to incorporate the resistance concept into the time-dependent problem? How are we going to combine the resistance concept with time-dependent problem? So this is the unique aspect of this problem. So in the previous case, to be able to check the validity of the lump capacitance method, we define as a dimensionless variable a BO number, which is H over LC, so H LC over K. So in this case, I need to modify H to include resistance. So if you just think about it, if you want to draw it in a large scale, we have convection here. I'm magnifying it. This is the ceramic layer. This is anti-corrosion material. And we have the steel. So the convection is happening on the outermost surface, and we are treating this, in this case, I'm choosing the control volume here. In this case, I'm choosing this as the control volume. Okay, steel is the control volume. I'm excluding ceramic in the system, so steel is the control volume. So when we talk about resistance concept, I introduced you a variable called overall heat transfer coefficient. Overall heat transfer coefficient. So in this case, we want to use this concept to be able to consider the effect of resistance. So 1 over U is equal to 1 over H plus R ceramic. So this is the equality. So we have two resistances, convective resistance per unit area, and we have contact resistance between ceramic and ceramic and steel. So the total resistance, this is equal to R total. So 1 over R total is overall heat transfer coefficient. So now we will substitute the values. 1 over U, and H is given to be 1 over 25 watt meter square per Kelvin, and our ceramic is given to be 0.01 meter square Kelvin over watt. So we have, if we add everything, we have 0.05 meter square Kelvin over watt. So that means U is 1 over 0.05, which is 20 watt meter square per Kelvin. Again, this has units of the same units with units of H, as you can imagine here. So this, as you can see here, this is units of H. So we now found an effective heat transfer, convective heat transfer coefficient for the system, which is U. So the BO number will be replaced by U LC over K. And in this case, LC is the thickness of the cylinder. This is LC. Because we have asymmetric situation, we have insulation on one side, we have convection on the other side. It is asymmetric, so we'll use this full length. So we have 20 watt meter square per Kelvin. The length is 0.01 meter. This is asymmetric here. We are not taking the half. And then I'm dividing this by the thermal conductivity of the steel, which is 60. And then if you carry out the math, you'll see that the BO number is less than 0.1. Now, this is good news for us. That means I can use the lump capacitance method. That is going to make the analysis fairly straightforward. So again, in this case, we only have convection. So for part A, so it is convection only. And we just draw the equation in the example or also in the slides. So we will be using that equation as it is, with one difference. We will be replacing H with U. So this is the equation that we already derived. Exponential minus U times T over rho LC CP. Okay? And again here, H is replaced by U. So in this case, that is the main difference here. And I'm interested in finding the time to reach 1200 degrees Celsius. So I will rearrange this equation. I'm interested in finding time to reach 1200 degrees Celsius. So everything here is a number, so we'll just substitute. The density is 1780, again kilogram per meter cube. The LC is 0.01 meter. CP is 430 joule kilogram per Kelvin. U is 20 watt per meter square Kelvin. And then we have log 1200 minus 1300 minus 300 minus 1300, and then we have all the variables here. So if you carry out this, you'll have 3886 seconds. That is how long it's going to take to reach for steel to reach 1200 Kelvin. So that was part A. In part B, we are interested in, let's say this is steel, this is ceramic, and we have the contact resistance here. What is the temperature here? Let's say this is T2. What is the temperature here at this particular time? So it is steady state problem. So that means if we do an energy balance, so energy coming in from convection has to go through the same Q everywhere. If this is Q, if this heat is coming from gas to the ceramic is Q, it has to go through the ceramic at Q, and from ceramic to steel as a Q. So that means H times T infinity minus T2 is equal to Q over A, or Q double prime, which is equal to T2 minus T1 over R ceramic. And we are told that the capacitance of the ceramic is negligible. We only consider the thermal contact resistance. So this means T2 minus T1 divided by R ceramic. So we are interested in finding T2 here. We have T2 here, so we equate these two terms to each other, and we will find T2 here. So T2 is H times T infinity plus T1 over R resistance, contact resistance of ceramic, divided by H plus 1 over R ceramic. And if you plug in the numbers, you'll have 1220 Kelvin. Okay, so T2 is outer surface, T1 is inner surface. This is the one that we just calculated. This was 1200. Okay, so as you can see, 1200 versus 1220 is not very different. So in other words, the thermal heat transfer is not significantly influenced by the furnace. So furnace is effectively heating the gas in the chamber, but it is also being protected against corrosion. So this is the main idea behind this analysis.